Hello there. Come on in and make yourself comfortable. You found Science Blanket, your quiet space for wonder, and I am so glad you've joined me tonight. Have you ever wondered how something can be as light as a feather, yet stronger than a beam of steel? Tonight, we're wrapping ourselves in the story of carbon fiber, a material that feels like it belongs in the future, yet had its humble beginnings in the glowing filaments of the very first light bulbs. We often think of strength as something heavy and solid, but carbon fiber shows us a different kind of power, a microscopic architecture of carbon atoms woven into a silent, shimmering lattice that is 70% lighter than metal. It's the material of satellites, racing cars, and deep-sea explorers, all held together by a structure as delicate as a spider's silk. As we begin, imagine a vast, dark honeycomb of hexagonal patterns stretching out into the darkness like a soft, geometric web. You don't need to calculate its density or understand its manufacturing yield tonight. Just let the idea of this invisible, weightless strength tuck you in. If this blanket of modern wonder helps you find rest, I'd love for you to subscribe and join our community of sleepy minds. It helps us keep the lights low and the stories flowing for everyone in search of peace. Now, let's take a slow, deep breath together. As you exhale, feel the weight of the day lifting off your chest, leaving you feeling as light and airy as the fibers we're discussing. Relax your brow, let your hands fall still, and allow your bed to support you completely. You don't need to hold anything up anymore. You can simply let go. Let's explore the silent strength of carbon fiber together. Carbon fiber is a material made primarily of carbon atoms arranged in strong crystalline structures, and when you think about it, there's something almost poetic about how nature's most fundamental building blocks can be transformed into one of the strongest materials we've ever created. The very name carbon fiber traces its roots back through centuries of language, all the way to the Latin word carbo, which means coal. It's a fitting connection, really, because both coal and carbon fiber share that same essential element, though they couldn't be more different in their properties and applications. Where coal crumbles and burns, carbon fiber holds firm with remarkable tenacity. If you were to examine carbon fibers under a powerful microscope, you'd discover something fascinating. The fibers consist of stacked flat microcrystals, all aligned parallel to the fiber axis, like thousands of tiny sheets of paper arranged in perfect order. This isn't random. This careful arrangement is what gives carbon fiber its extraordinary properties. The carbon atoms form a hexagonal lattice structure, and this particular geometric pattern is key to understanding why carbon fiber performs so remarkably well. Think of it like a honeycomb, where each hexagon shares its walls with neighboring hexagons, creating a network of mutual support that's incredibly difficult to break apart. This hexagonal lattice structure provides steel-like strength at a fraction of the weight, which is perhaps the most celebrated characteristic of carbon fiber. When engineers and designers talk about carbon fiber, this strength-to-weight ratio is usually the first thing they mention, and for good reason. Carbon fiber has a density of about 1,800 kilograms per cubic meter, which might sound like a lot until you compare it to steel. Steel is significantly denser, which means that for the same volume, carbon fiber weighs considerably less. This difference might not seem like much on paper, but in practical applications, it changes everything. Consider this remarkable comparison. Carbon fiber is about 5 times stronger than steel while being roughly 70% lighter. Let that sink in for a moment. Imagine holding a steel rod in one hand and a carbon fiber rod of the same dimensions in the other. The carbon fiber rod would feel almost impossibly light by comparison, yet if you tried to break both, you'd find the carbon fiber far more resistant to failure. This paradox of lightness and strength has revolutionized industries from aerospace to sports equipment, allowing engineers to build structures that were simply impossible before carbon fiber became widely available. But the story gets even more impressive when we look at specific measurements. The tensile strength of carbon fiber, which is its ability to resist being pulled apart, can be 7 times greater than steel at 1/4 the weight. Think about what this means in practical terms. A cable made of carbon fiber could lift the same load as a steel cable 7 times its strength, while weighing only 1/4 as much. For applications where every gram matters, like in aircraft or racing vehicles, this difference isn't just significant, it's transformative. It's the difference between what's possible and what's merely theoretical. Engineers measure the stiffness of materials using something called the elastic modulus, which tells us how much a material will deform under stress. Carbon fiber has an elastic modulus ranging from 200 to 600 gigapascals, depending on the specific type and manufacturing process. To put this in perspective, materials with higher elastic moduli don't bend or stretch as easily under load. They maintain their shape even when forces are applied to them. This makes carbon fiber ideal for applications where precision and dimensional stability are crucial, like in telescope mirrors or precision instruments that can't afford to flex or warp. And if you think those numbers are impressive, consider this. Ultra-high modulus variants of carbon fiber can reach stiffness levels up to 900 gigapascals. These specialized forms of carbon fiber represent the pinnacle of material engineering, pushing the boundaries of what's physically possible. They're used in the most demanding applications imaginable, places where failure isn't just inconvenient but potentially catastrophic. These ultra-high modulus fibers cost more and require more sophisticated manufacturing processes, but for certain applications, nothing else will do. However, carbon fiber isn't perfect, and understanding its limitations is just as important as celebrating its strengths. While carbon fiber excels at resisting tension, pulling forces, its compressive strength, its ability to resist being crushed or compressed, is lower than its tensile strength. This asymmetry in properties requires careful structural design. Engineers can't simply substitute carbon fiber for steel and expect everything to work the same way. They need to think differently, to design structures that take advantage of carbon fiber's incredible tensile strength while protecting it from excessive compression. This often means using carbon fiber in combination with other materials, creating composite structures where each material does what it does best. This characteristic of lower compressive strength has led to some innovative engineering solutions. In aerospace applications, for instance, designers often use sandwich structures where carbon fiber skins are separated by lightweight cores. This configuration maximizes the use of carbon fiber in tension while the core handles compressive loads. It's a perfect example of how understanding a material's limitations can lead to creative solutions that actually improve overall performance. The limitation becomes not a weakness but an opportunity for clever design. The hexagonal arrangement of carbon atoms in carbon fiber creates bonds that are extraordinarily strong, and these bonds are directional, meaning they're strongest along the length of the fiber. This is why carbon fiber performs so well in tension along its axis but less well in compression or in directions perpendicular to the fiber. Understanding this directionality is crucial for anyone working with carbon fiber. It's not an isotropic material like steel, which has similar properties in all directions. Carbon fiber is highly anisotropic, with properties that vary dramatically depending on the direction of loading. This means that the orientation of fibers in a composite part is just as important as the properties of the fibers themselves, and skilled composite designers spend considerable time determining the optimal layout patterns for each specific application. Individual carbon fiber filaments are extremely thin, measuring about 0.005 to 0.010 of a millimeter in diameter. To give you some perspective on just how thin that is, a human hair is typically about 70 micrometers in diameter, which means these carbon filaments are roughly 7 to 14 times thinner than a single strand of your hair. If you were to hold one between your fingers, you probably wouldn't even feel it. It would be nearly invisible to the naked eye, a gossamer thread that seems too delicate to possess any strength at all. Yet this is where the magic of carbon fiber begins, in these impossibly thin filaments that, when combined properly, create something extraordinary. These individual filaments are never used alone. Instead, they're bundled together into what's called a tow, and each strand or tow contains between 3,000 and 6,000 individual filaments, all aligned parallel to each other. Imagine 3,000 individual threads, each one thinner than anything you could easily see, all gathered together and running in the same direction. This bundling is essential because while each individual filament has impressive properties, it's the collective strength of thousands of filaments working together that makes carbon fiber so useful. The tow itself still looks quite thin, almost like a piece of yarn or embroidery thread, but it contains within it the combined strength of all those thousands of fibers. What's particularly interesting is that carbon fiber doesn't just have mechanical properties that make it special. It also conducts electricity, which might surprise you if you're used to thinking of fibers and textiles as insulators. The same carbon atoms that give the material its strength also allow electrons to flow through it relatively easily. This electrical conductivity opens up some fascinating applications beyond simple structural uses. Carbon fiber can shield against electromagnetic interference, making it valuable in electronics and aerospace applications where stray electromagnetic signals could cause problems. Imagine wrapping sensitive electronic equipment in a material that's both incredibly strong and capable of blocking unwanted electromagnetic radiation. That's exactly what carbon fiber allows us to do. The electrical properties of carbon fiber have led to some creative applications over the years. It's been used in everything from smartphone cases that protect against electromagnetic interference to aircraft structures that need to handle lightning strikes without damage. When lightning hits an aircraft made with carbon fiber composites, the material needs to conduct that massive electrical charge safely around passengers and sensitive systems. Engineers have had to develop special techniques to ensure carbon fiber structures can handle these electrical loads, sometimes incorporating metal mesh or other conductive elements to create safe pathways for electricity to follow. Just as carbon fiber conducts electricity in interesting ways, it also has unique thermal properties. It conducts heat efficiently along the fiber direction, meaning heat flows readily from one end of a fiber to the other. But here's where it gets fascinating. Carbon fiber insulates across fibers perpendicular to their length. This directional difference in thermal conductivity mirrors the directional differences we see in mechanical strength. Heat flows easily along the axis where the carbon atoms are tightly bonded in their hexagonal lattice, but struggles to move from fiber to fiber across that organized structure. This property can be incredibly useful in applications where you want to move heat in one direction but not others, like in heat sinks for electronics or thermal management systems in spacecraft. Perhaps one of the most remarkable thermal properties of carbon fiber is its extremely low thermal expansion coefficient, which is very close to zero. Most materials expand when heated and contract when cooled. Metal bridges expand in summer heat and contract in winter cold. Railroad tracks are laid with tiny gaps to accommodate this expansion. But carbon fiber barely changes dimension with temperature at all. This dimensional stability makes it ideal for precision applications where even tiny changes in size could cause problems. Telescope mirrors, for instance, need to maintain their exact shape regardless of temperature changes as they scan from one part of the sky to another. Satellite structures need to remain precisely dimensioned even as they move from the searing heat of direct sunlight to the frigid cold of Earth's shadow every 90 minutes. This near-zero thermal expansion becomes even more impressive when you consider the extreme temperatures that carbon fiber can withstand. Carbon fiber melts at temperatures around 3,500 degrees Celsius. To put that in context, steel melts at around 1,500 degrees Celsius, aluminum at about 660 degrees. The surface of the Sun is about 5,500 degrees. Carbon fiber can withstand temperatures that would turn most other materials into puddles or vapor, remaining solid and maintaining its properties in conditions that are difficult to even imagine. This extreme temperature resistance makes carbon fiber invaluable for applications like rocket nozzles, heat shields, and brake systems that need to function in extraordinarily hot environments. Beyond its temperature resistance, carbon fiber remains chemically stable and highly resistant to corrosion. Steel rusts when exposed to moisture and oxygen. Aluminum corrodes in salt water. Many plastics degrade when exposed to ultraviolet light or certain chemicals. But carbon fiber simply sits there, unaffected by most of what the world can throw at it. It doesn't rust because it's not a metal. It doesn't rot because it's not organic in the traditional sense. It doesn't react with most acids, bases, or solvents that would damage other materials. This chemical inertness means that carbon fiber structures can last for decades in harsh environments without protective coatings or constant maintenance. This corrosion resistance has made carbon fiber particularly attractive for marine applications, chemical processing equipment, and structures exposed to harsh weather. Boats made with carbon fiber don't need the constant maintenance that traditional materials require. Chemical tanks can hold aggressive substances without degrading. Infrastructure in coastal areas can withstand salt spray that would quickly corrode metal. The material simply endures, unchanging and reliable, asking nothing more than to be left alone to do its job. Carbon fiber also exhibits high fatigue resistance, surviving millions of stress cycles without the kind of degradation that plagues metals. Fatigue is what happens when you bend a paper clip back and forth repeatedly until it snaps. The material weakens with each cycle of stress until it finally fails. This is a major concern in applications like aircraft wings or rotating machinery, where components experience thousands or millions of stress cycles over their lifetime. Carbon fiber handles these repeated stresses remarkably well, maintaining its strength and stiffness through cycle after cycle. Engineers can design carbon fiber components to last through the entire service life of a product without worrying about fatigue failure, something that's much harder to achieve with metals. In fact, products made from undamaged carbon fiber can last virtually indefinitely. If you protect carbon fiber from impact damage and excessive UV exposure, there's no fundamental reason it should ever wear out. The carbon atoms aren't going anywhere. They're not reacting with their environment. They're not slowly weakening with time. This longevity means that carbon fiber structures built today could still be functioning centuries from now, a kind of permanence that's rare in our world of planned obsolescence. It's a material that, once made, persists, carrying forward the strength and precision of its creation into an indefinite future. Carbon fiber was first used in light bulb filaments in the 1860s, which might come as a surprise if you think of carbon fiber as a modern material. More than a century and a half ago, inventors were already experimenting with carbon in fiber form, though their purposes and methods were quite different from what we know today. These early pioneers were searching for something that could glow brightly when electricity passed through it, and they found that carbonized natural fibers could do exactly that. It wasn't the high-performance structural material we use today, but it was carbon, it was fibrous, and it represented humanity's first serious attempt to harness this element in a form that would eventually change the world. Early carbon filaments were patented by Joseph Swan and Thomas Edison, two names that have become synonymous with the invention of the electric light bulb. Both men worked independently on similar problems, trying to create a filament that would glow without burning up too quickly. Swan, working in England, and Edison, working in America, both experimented with carbonized threads and fibers. Edison famously tested thousands of materials before settling on carbonized bamboo, which could last for hundreds of hours. These early carbon filaments were made by taking natural fibers, cotton thread, or bamboo, and heating them in an oxygen-free environment until everything but the carbon had been driven off. The result was a fragile, glowing thread that made electric lighting practical for the first time. Of course, these early carbon filaments bore little resemblance to modern carbon fiber. They were brittle, inconsistent, and their properties varied wildly depending on the source material and processing conditions. But they established an important principle, that carbon in fibrous form had unique and valuable properties. As the 20th century progressed and tungsten filaments replaced carbon in light bulbs, carbon fibers largely disappeared from public consciousness. They became a historical footnote, an interesting dead end in the story of electric lighting. But the fundamental idea remained, waiting for someone to rediscover it and push it in new directions. That rediscovery came when the first modern high-performance carbon fibers were invented in 1958. This was a completely different approach from those early light bulb filaments. Researchers were no longer trying to make something that would glow, they were trying to make something that would hold together under extreme stress. The breakthrough came from understanding that if you could control the process carefully enough, you could create fibers where the carbon atoms were arranged in highly organized structures, those hexagonal lattices we talked about earlier. This wasn't accidental carbonization anymore. This was precision engineering at the molecular level, deliberately creating structures with specific properties. REN was the earliest precursor material before newer methods emerged, and this makes sense when you think about it. REN is a fiber made from cellulose, which is itself rich in carbon. Researchers discovered that if they took REN fibers and subjected them to carefully controlled heat treatments, they could drive off everything except the carbon, leaving behind fibers with impressive strength and stiffness. The process was tricky, requiring precise control of temperature, atmosphere, and tension, but it worked. Those early REN-based carbon fibers showed enough promise that researchers around the world began investigating the technology, looking for ways to improve the process and reduce costs. However, REN had limitations as a precursor material. The yield wasn't great, meaning much of the starting material was lost during processing, and the properties of the resulting carbon fibers, while impressive, weren't quite as good as researchers hoped they could be. So the search continued for better precursor materials, substances that would convert more efficiently into high-quality carbon fiber. This search led to the material that now dominates the industry. Today, about 90% of carbon fibers are made from polyacrylonitrile precursors, usually just called PAN. Polyacrylonitrile is a synthetic polymer, essentially a type of plastic, that has just the right chemical structure to convert efficiently into organized carbon fiber. The production process involves oxidation, carbonization, and graphitization, three distinct stages that transform the precursor material into finished carbon fiber. During oxidation, the precursor fibers are heated in air to temperatures around 200 to 300 degrees Celsius. This causes chemical changes in the polymer that stabilize it and prepare it for the next stage. The fibers turn dark and become more rigid as oxygen atoms are incorporated into their structure. This oxidation step is slow and carefully controlled because if it happens too quickly, the fibers can become damaged or develop defects that will weaken the final product. After oxidation comes carbonization, where the stabilized fibers are heated to much higher temperatures, typically between 1000 and 2000 degrees Celsius, but this time in an inert atmosphere without oxygen. At these extreme temperatures, atoms other than carbon, primarily nitrogen and hydrogen, are driven off as gases, leaving behind a structure that's increasingly pure carbon. The carbon atoms begin to organize themselves into those characteristic hexagonal planes, stacking together in the highly ordered arrangement that gives carbon fiber its strength. The fibers shrink during this process as non-carbon elements escape, becoming denser and stronger. Fibers are graphitized at temperatures above 2000 degrees Celsius to align carbon atoms even more perfectly. Graphitization is an optional final step used for the highest performance carbon fibers. At these extreme temperatures, well above the melting point of most metals, the carbon atoms have enough thermal energy to rearrange themselves into nearly perfect crystalline structures. The hexagonal planes align more precisely, defects are reduced, and the resulting fiber has even higher stiffness and better electrical and thermal conductivity. Not all carbon fibers undergo graphitization because it's expensive and time-consuming, but for applications that demand the absolute best performance, it's worth the extra effort and cost. Despite all this sophisticated processing, the manufacturing yield from precursor material is only about 50%. That means that for every kilogram of precursor fiber that enters the production line, only about half a kilogram of finished carbon fiber emerges at the end. The rest is lost as gases driven off during oxidation and carbonization, or as material that doesn't meet quality standards and must be discarded. This low yield contributes to the high cost of carbon fiber in a very direct way. If you need to buy 2 kilograms of precursor material to get 1 kilogram of finished product, your material costs are immediately doubled before you even consider the energy and equipment costs. And those energy costs are substantial. Producing carbon fiber consumes energy comparable to aluminum smelting, which is one of the most energy-intensive manufacturing processes in existence. Those high temperatures, the furnaces running at 2000 degrees or more for hours at a time, require enormous amounts of electricity. The controlled atmospheres, the careful monitoring, the slow processing speeds, all of these add to the energy requirements. When you consider that we're heating materials to temperatures where most substances would vaporize, maintaining those conditions for extended periods, it becomes clear why carbon fiber manufacturing facilities have such large energy footprints. This energy intensity, combined with the low yield from precursor materials, explains why carbon fiber remains expensive compared to traditional materials like steel or aluminum, even as manufacturing technology has improved and production volumes have increased over the decades. Carbon fiber is typically combined with epoxy resin to form a composite material, and this combination is where carbon fiber truly comes into its own as an engineering material. The fibers themselves, those bundles of thousands of individual filaments we talked about earlier, are impressive on their own, but they need something to hold them in place, to transfer loads between fibers, and to protect them from damage. That's where the resin comes in. Epoxy resin surrounds each fiber, fills the spaces between them, and hardens into a solid matrix that locks everything together. The result is a composite material where the fibers provide strength and stiffness while the resin holds everything in the right position and distributes forces throughout the structure. Think of it like reinforced concrete, where steel bars provide tensile strength while concrete provides compressive strength and holds the bars in position. Carbon fiber composites work on a similar principle, though the scale is much smaller and the properties are quite different. The fibers can only carry loads effectively if they're held firmly in place, prevented from buckling or sliding past each other. The resin does this job, acting as a matrix that keeps fibers aligned and working together. Without the resin, you just have a bundle of loose fibers that couldn't maintain any particular shape or carry any significant load. With the resin, you have a solid material that can be shaped into complex forms and engineered to have specific properties. This composite can be engineered to be stiff or flexible depending on weave and treatment, which is one of the most powerful aspects of working with carbon fiber. Unlike metals, which have fixed properties determined by their composition and heat treatment, carbon fiber composites can be tailored to meet specific requirements. Need something extremely rigid that won't flex at all? You can do that. Need something that can bend and spring back? You can do that too. The key is understanding how fiber orientation, weave pattern, resin selection, and curing process all interact to create the final properties. It's almost like having a material that you can tune like a musical instrument, adjusting its characteristics to produce exactly the performance you need. Unidirectional fibers are strongest along their primary axis, which makes intuitive sense when you remember that carbon fiber's strength comes from the way carbon atoms are bonded along the length of each fiber. When all the fibers run in the same direction, all of those strong bonds are aligned with each other, pulling together in the same direction. This creates maximum strength and stiffness along that axis. Unidirectional composites are used when loads are predictable and come from a specific direction, like in bicycle frames where the main tubes experience tension and compression along their length, or in aircraft spars where bending loads create stresses along the length of the component. However, unidirectional fiber arrangements have an obvious weakness: they're much weaker in other directions. If you try to pull perpendicular to the fibers, you're relying entirely on the resin to carry the load, and resin is much weaker than carbon fiber. This is where woven fabrics come in, creating two-dimensional reinforcement that provides strength in multiple directions. Twill weave carbon fiber uses a diagonal pattern that improves shape retention, with fibers weaving over and under each other in a pattern that creates that characteristic diagonal appearance you've probably seen on everything from car parts to bicycle components. The twill pattern, usually a 2/2 underweave, allows the fabric to drape and conform to complex shapes more easily than other weave patterns. This drapability is crucial when you're trying to lay carbon fiber fabric into molds with compound curves and complex geometries. The twill weave allows the fabric to shift and adjust, to nestle into tight corners and stretch over convex surfaces without wrinkling or bunching up. Those wrinkles and bunches would create weak spots in the final composite, so the weave pattern's ability to conform cleanly to complex shapes directly translates into stronger, more reliable parts. The diagonal pattern also tends to distribute loads in an interesting way, spreading stresses across the weave rather than concentrating them along fiber directions. Plain weave offers balanced strength but slightly less flexibility than twill, using a simple over-one under-one pattern that creates a checkerboard appearance. This is the most basic weave pattern, the same one used in common fabrics like bed sheets, but executed with high-performance carbon fiber tows. Plain weave provides nearly equal strength in both the lengthwise and crosswise directions because fibers are distributed evenly in both orientations. This balanced strength is valuable in applications where loads might come from multiple directions or where the exact loading conditions aren't perfectly predictable. However, the tight, frequent crossovers in plain weave make the fabric stiffer and less able to drape into complex shapes compared to twill weave. The choice between plain weave and twill weave, or other weave patterns, depends on what matters most for a particular application. Are you building something with complex curves where drapability is critical? Twill might be your choice. Are you building something relatively flat where balanced properties in all directions matter most? Plain weave could be better. These decisions happen thousands of times in the design of any complex carbon fiber structure, with engineers selecting specific weave patterns for specific areas based on the local requirements. Within the world of carbon fiber itself, before we even consider weave patterns, there are different grades with different characteristics. High modulus fibers prioritize stiffness rather than maximum tensile strength, using more aggressive heat treatment during manufacturing to create more perfect crystalline structures. These fibers bend less under load, maintaining their shape with remarkable rigidity. They're used in applications like aerospace structures and precision instruments where deflection under load must be minimized. A telescope mount that flexes even slightly will produce blurry images. A robot arm that bends under its own weight won't position things accurately. High modulus carbon fiber solves these problems by simply refusing to bend. The trade-off is that high modulus fibers tend to be more brittle, with lower ultimate tensile strength than standard fibers. They don't stretch as much before breaking, which can be a disadvantage in applications where impact resistance matters. This has led to the development of intermediate modulus fibers that balance stiffness and strength for sporting applications like tennis rackets, fishing rods, and bicycle frames. These fibers offer better stiffness than standard carbon fiber but retain more of that ultimate strength and some of the toughness that makes standard carbon fiber more forgiving of impacts and overloads. It's a compromise, but often a very useful one. The resin component of carbon fiber composites has its own important characteristics. Carbon fiber composites can flex under heat and recover upon cooling, a property that comes primarily from the thermoplastic or thermoset resin rather than the fibers themselves. The fibers remain essentially unchanged up to very high temperatures, but the resin can soften when heated, allowing the composite to be formed or reformed. Some manufacturers use this property intentionally, heating carbon fiber composites to mold them into complex shapes, then cooling them to lock those shapes in place. This thermoplastic behavior opens up possibilities for repair and recycling that wouldn't exist with purely thermoset resins that can't be softened once cured. On the other end of the temperature spectrum, cold temperatures can make the resin more rigid and the composite more brittle. As temperatures drop, the polymer chains in the resin move less freely, and the material becomes stiffer and more prone to cracking under impact. This is generally more of a concern with certain types of resin than with the carbon fibers themselves, which maintain their properties well even at cryogenic temperatures. Engineers designing carbon fiber structures for cold environments need to select resins carefully and conduct extensive testing to ensure the composite will maintain adequate toughness even in the coldest conditions it might encounter. Finally, the interface between fiber and resin deserves attention. Surface sizing agents are applied to fibers to improve bonding with resin, creating a chemical bridge between the two materials. Without these sizing agents, the smooth surface of carbon fibers wouldn't bond well with resin, and the composite would be weak because fibers could pull out of the matrix under load. Sizing agents are carefully formulated to match specific resin systems, creating chemical bonds or mechanical interlocking that ensures fibers and resin work together as one material rather than two materials that just happen to be in contact. This interface is invisible in the finished composite, but it's absolutely critical to performance, the glue that makes everything else work. Most carbon fiber components are made by layering sheets by hand, which might come as a surprise in our age of automation and advanced manufacturing. You might imagine robotic arms precisely placing carbon fiber with computer-controlled accuracy, but the reality in most workshops and even many factories is quite different. Skilled technicians take sheets of carbon fiber fabric, cut them to size and shape, and carefully lay them into molds one layer at a time. They smooth out air bubbles, ensure proper alignment, and build up the thickness gradually until the part has the right number of layers. It's painstaking work that requires attention to detail and considerable experience to do well. Each layer matters, and the orientation of fibers in each layer contributes to the final properties of the component. This hand layup process has persisted not because the industry hasn't tried to automate it, but because carbon fiber composites present unique challenges that make automation difficult. The materials are delicate, the shapes are often complex, and the requirements for quality are extremely high. A single wrinkle or air pocket can compromise a part's strength, and detecting these defects requires human judgment and touch. Experienced technicians can feel when something isn't right, when a layer isn't lying flat or when the fabric isn't conforming properly to the mold. They can make small adjustments on the fly, adding a bit more pressure here, smoothing out a bubble there, in ways that are difficult to program into a machine. Automation is mainly used for cutting rather than full fabrication, because cutting is a task that machines can do extremely well. Computer-controlled cutters can take a digital pattern and reproduce it perfectly in carbon fiber fabric, time after time with no variation. They can cut complex shapes with curved edges and intricate details, and they can do it far faster than a human with scissors. This automation at the cutting stage saves time and reduces waste, ensuring that each piece is exactly the right size and shape before it goes to the technicians for layup. But once those pieces are cut, they still need human hands to position them correctly and ensure they're properly integrated into the composite structure. There are different methods for getting the resin into the carbon fiber fabric, and each has its advantages. Wet layup involves soaking fibers in resin before placing them in molds, a process that's straightforward and flexible. The technician literally paints or pours resin onto the dry carbon fiber fabric, working it in with brushes or rollers to ensure complete saturation. Then they place the wetted fabric into the mold, add the next layer, and repeat the process. Wet layup allows for a lot of flexibility in terms of resin choice and fiber-to-resin ratio, and it doesn't require expensive pre-made materials. The downside is that it can be messy. The resin-to-fiber ratio can vary from part to part or even within a single part, and you're working with materials that have a limited pot life once the resin and hardener are mixed. For more consistent results, many manufacturers use prep-reg carbon fiber, which comes pre-impregnated with resin for consistency. Prep-Reg looks like sheets of carbon fiber fabric, but if you touch it, you'll find it slightly tacky and has a uniform, semi-stiff feel. The resin has already been applied in a controlled factory environment, ensuring that every square inch of fabric has exactly the right amount of resin. This consistency translates directly into more predictable properties in the finished part. Prep-Reg also tends to be cleaner to work with than wet layup, with no messy mixing of resin or dripping as you transfer fabric to the mold. The layers stick to each other slightly, making it easier to build up a laminate without having layers shift out of position. However, Prep-Reg material has limited shelf life unless stored at low temperatures, typically requiring freezer storage at around -18 degrees Celsius. The resin in Prep-Reg is already mixed with its hardener, and even though curing is delayed, it's slowly progressing even at room temperature. Leave Prep-Reg sitting at room temperature for too long, and it will begin to harden, becoming stiff and eventually unusable. This is why shops that use Prep-Reg have dedicated freezers, and why they carefully track how long each roll has been out of the freezer. Material that's been out too long or stored improperly may not cure correctly, leading to weak parts. The need for cold storage adds complexity and cost to working with Prep-Reg, but for critical applications where consistency matters more than convenience, it's worth it. One of the appealing aspects of carbon fiber is its appearance, and patterns can be customized through weaving, printing, or laser engraving. The distinctive look of carbon fiber, with its woven texture and subtle sheen, has become associated with high performance and advanced technology. Some manufacturers customize this appearance by using different weave patterns, creating visual interest while maintaining structural integrity. Others print designs onto the surface of carbon fiber or use laser engraving to add logos, text, or decorative elements. These customizations are often purely aesthetic, not affecting the structural properties of the material, but they allow manufacturers to create distinctive products and give consumers the visual experience they've come to expect from carbon fiber components. There's also a common misconception that carbon fiber must be black. While raw carbon fiber is indeed black, carbon fiber can be produced in colors beyond black using coatings or resins. Colored resins can be used in the layup process, creating composites where the matrix is blue, red, green, or any other color while the carbon fibers themselves remain black. This creates an interesting visual effect where you can still see the fiber weave but with a colored tint. Alternatively, painted or powder-coated finishes can be applied to the surface of cured carbon fiber parts, completely changing their appearance. Some manufacturers even use colored fibers themselves, though these are typically specialty products that combine carbon with other materials. Like any material, carbon fiber components can be damaged, and knowing how to address that damage is important for owners and manufacturers alike. Minor damage can be repaired with epoxy fillers and patches, particularly surface scratches or small areas where the outer layers have been abraded but the underlying structure remains intact. These repairs typically involve sanding the damaged area to create a clean, rough surface, then building up the damaged section with epoxy filler or additional layers of carbon fiber fabric. Once cured and sanded smooth, such repairs can restore much of the component's original strength and appearance. For non-critical applications, these repairs can be done by reasonably skilled individuals with the right materials and some patience. However, severe damage typically requires professional repair or replacement. If a carbon fiber component has been seriously impacted, cracked through multiple layers, or damaged in a way that affects its structural integrity, amateur repairs are risky. Carbon fiber doesn't always show damage the way metals do. A metal part might dent or bend visibly, but carbon fiber can have internal delamination or fiber breakage that's not obvious from the surface. Professional repair facilities have the equipment to properly assess damage, determine whether repair is feasible, and execute repairs that restore the component to its original specifications. They can also test repaired components to ensure they meet strength requirements, something that's difficult to do outside a proper facility. As carbon fiber becomes more common, the question of what happens to it at the end of its life becomes increasingly important. Recycling carbon fiber often involves pyrolysis to recover usable fibers, a process that heats the composite in an oxygen-free environment to burn away the resin while leaving the carbon fibers intact. The recovered fibers are shorter and more random than virgin carbon fiber, and they generally have lower mechanical properties, but they're still valuable and can be used in less demanding applications. This pyrolysis process is energy intensive, though less so than producing virgin carbon fiber, and the recovered fibers need to be processed into new forms before they can be used again. As the carbon fiber industry matures, recycling is becoming more economically viable, and we're seeing more companies that specialize in recovering and reprocessing carbon fiber from end-of-life components. Carbon fiber revolutionized the aerospace industry by drastically reducing weight, and it's difficult to overstate just how transformative this has been. In aerospace, weight is everything. Every kilogram you add to an aircraft means more fuel needed to lift it, more powerful engines required to move it, and ultimately less payload capacity or shorter range. Engineers have always fought to shave grams wherever possible, using exotic alloys, hollowing out structural members, and optimizing every component. Then carbon fiber arrived and offered something unprecedented: the ability to reduce weight by 30, 40, even 50% in certain components without sacrificing strength. It was like finding a cheat code for aircraft design, suddenly making possible designs that had been theoretical dreams. The impact wasn't just about making existing aircraft lighter. Carbon fiber enabled entirely new approaches to aircraft design. Structures could be made larger and more efficient because the weight penalty wasn't as severe. Wings could be longer and more slender, improving aerodynamic efficiency. Fuselages could have larger diameters, creating more spacious cabins without weight spiraling out of control. Engineers could pursue optimizations that would have been impossible with aluminum or steel because the weight would have become unmanageable. Carbon fiber didn't just improve aircraft, it changed what was possible to build in the first place. Modern aircraft structures can be more than 50% carbon fiber composites, a proportion that would have seemed impossible just a few decades ago. The Boeing 787 Dreamliner, for instance, uses carbon fiber extensively throughout its structure, in the wings, fuselage, tail surfaces, and many other components. Walk around a modern airliner and you're looking at a machine where carbon fiber has become the primary structural material rather than an exotic specialty item. This represents an enormous shift in aerospace manufacturing, requiring new production techniques, new quality control methods, and new approaches to design and certification. The industry essentially had to reinvent itself to take full advantage of what carbon fiber offers. The benefits of this transformation extend beyond just the initial weight savings. Using carbon fiber can reduce aircraft fuel consumption by up to 20% compared to equivalent aluminum designs. That 20% isn't just about the lighter weight, though that's certainly a major factor. It also comes from the ability to optimize aerodynamics when weight constraints are relaxed, to use more efficient engine placements, and to design structures that maintain their shape more precisely under load. 20% fuel savings might not sound dramatic until you consider that a large airliner can burn thousands of liters of fuel per hour. Over the life of an aircraft spanning decades and millions of kilometers, that 20% savings translates into enormous reductions in fuel costs and carbon emissions. The applications of carbon fiber in aerospace are remarkably diverse. It is used in wings, fuselages, engines, and satellite components, each application taking advantage of different properties of the material. In wings, the combination of high strength and low weight allows for more efficient structural designs and better fatigue resistance. In fuselages, carbon fiber's corrosion resistance means less maintenance and longer service life. In engines, components made from carbon fiber composites can withstand high temperatures while keeping weight down, improving engine efficiency. In satellites, the material's dimensional stability and low weight are crucial for maintaining precise alignments in space while minimizing launch costs. Speaking of space applications, carbon fiber was used in the Hubble Space Telescope for thermal stability, helping ensure that this remarkable instrument could maintain its precise optical alignment despite the extreme temperature swings of orbiting Earth. The Hubble moves from blazing sunlight to deep shadow every 90 minutes or so, experiencing temperature variations that would cause most materials to expand and contract significantly. Such dimensional changes would have thrown the telescope's optics out of alignment, blurring the images that have become so iconic. Carbon fiber's near-zero thermal expansion coefficient meant that critical structural components maintained their exact dimensions regardless of temperature, allowing the telescope to deliver sharp images across decades of operation. Back on Earth, carbon fiber has found unexpected applications in medical technology. It is transparent to X-rays, making it useful in medical imaging equipment, particularly in X-ray and CT scanning tables. Traditional metal tables and supports would show up as bright areas on X-ray images, blocking the view of whatever tissue or bone lies behind them. Carbon fiber, however, appears essentially invisible to X-rays, allowing radiologists to see through the table as if it wasn't there. This transparency combined with carbon fiber's strength means that patient support tables can be strong enough to safely hold people while remaining completely out of the way of imaging systems. The material has enabled better imaging from more angles, improving diagnostic capabilities. In the energy sector, carbon fiber pressure vessels store hydrogen at extremely high pressures, sometimes exceeding 700 bar, which is about 700 times normal atmospheric pressure. Hydrogen has enormous potential as a clean fuel, but it's challenging to store efficiently because it has such low density. To get a useful amount of hydrogen into a reasonable volume, you need to compress it to extremely high pressures or cool it to cryogenic temperatures. Pressure vessels made from carbon fiber composites can handle these extreme pressures while remaining light enough to be practical for vehicles. The fibers wrap around the vessel in carefully designed patterns, creating a structure that can contain all that pressure without being impossibly heavy or bulky. Military applications have also embraced carbon fiber enthusiastically. It absorbs radar waves, making it valuable in stealth aircraft that need to minimize their radar signature. When radar energy hits a carbon fiber composite structure, much of that energy is absorbed by the material rather than being reflected back to the radar receiver. Combined with carefully designed shapes that deflect what radar energy isn't absorbed, carbon fiber helps create aircraft that are extremely difficult to detect. This radar-absorbing property is partly due to the electrical conductivity of carbon fiber, which causes radar energy to be converted to heat rather than reflected. It's yet another example of how the same material properties that make carbon fiber strong and light also provide unexpected benefits in specific applications. At the extreme end of aerospace performance, hypersonic vehicles use carbon fiber in leading edges to withstand extreme heat generated by moving through the atmosphere at speeds exceeding Mach 5. At these velocities, air friction creates temperatures that would melt most materials. The leading edges of wings and control surfaces, where the heating is most intense, need materials that can maintain their strength at temperatures exceeding 1,000 degrees Celsius. Carbon fiber composites, particularly those using special high-temperature resins or carbon-carbon composites where even the matrix is carbon, can survive in these brutal conditions. They maintain their strength and shape even as the air around them reaches temperatures hot enough to glow. Looking forward, carbon fiber reinforced polymers are essential for modern space exploration, enabling missions that would be impossible with traditional materials. Whether it's the structural components of rockets that must be light enough to reach orbit yet strong enough to survive the stresses of launch, the habitat modules that will house astronauts on long-duration missions, or the mechanisms that must deploy reliably after months or years in the harsh environment of space, carbon fiber plays a crucial role. As humanity pushes further into space, to the Moon, to Mars, and beyond, the unique properties of carbon fiber will become even more critical. Every kilogram saved in structural weight is a kilogram that can be devoted to scientific instruments, life support systems, or fuel for the journey home. In the unforgiving environment of space, where failure means disaster and every resource is precious, carbon fiber's combination of strength, lightness, and stability makes it not just useful but indispensable. In automotive design, carbon fiber enables lighter, stronger vehicle structures, bringing to road cars the same benefits that transformed aerospace decades earlier. The automotive industry has always been obsessed with weight reduction, understanding that lighter vehicles accelerate faster, brake more effectively, handle better, and consume less fuel. For decades, this meant using aluminum instead of steel, removing unnecessary material, and accepting compromises between weight and strength. Carbon fiber changed the equation entirely, offering the possibility of structures that were both lighter and stronger than what came before. Early applications focused on racing and exotic supercars, but the technology has gradually spread to more mainstream vehicles as manufacturing costs have declined and production techniques have matured. The most critical application of carbon fiber in automobiles is in safety structures. Some car passenger cells are built almost entirely from carbon fiber composites, creating protective cages around occupants that are incredibly strong yet remarkably light. These passenger cells, sometimes called survival cells or safety cells, need to remain intact during crashes while the surrounding structure absorbs impact energy. Carbon fiber's high strength and controlled failure characteristics make it ideal for this purpose. When designed correctly, carbon fiber structures can absorb tremendous amounts of energy by fracturing in controlled ways, protecting occupants while keeping the weight down. High-end sports cars and supercars routinely use carbon fiber monocoques, single-piece structures that form the entire central chassis and provide mounting points for suspension, drivetrain, and body panels. The racing world pushed carbon fiber development hard and continues to do so. Formula One cars use over a ton of carbon fiber for chassis and aerodynamics, which might sound like a lot until you consider that these cars experience forces that would tear apart almost any other structure. A Formula One car generates several times its own weight in downforce at high speeds, pressing it into the track with forces that would crush ordinary materials. The chassis must be rigid enough to maintain precise suspension geometry under these loads while being light enough to accelerate and brake at rates that would be impossible with heavier materials. Every aerodynamic element, every wing and diffuser and end plate, is made from carbon fiber, shaped and optimized to manage airflow with micrometer precision. The history of carbon fiber in racing is a story of dramatic transformation. The first carbon fiber Formula One chassis debuted in 1981, when McLaren introduced the MP41 designed by John Barnard. At the time, it was revolutionary and somewhat controversial. Other teams were skeptical that carbon fiber could survive the rigors of racing. But the MP41 proved not only durable but superior to the aluminum monocoques it competed against. It was stiffer, lighter, and provided better crash protection. Within a few years, every competitive Formula One team had switched to carbon fiber chassis, and the material became mandatory for modern racing. That first carbon fiber Formula One car didn't just win races, it changed motorsport forever. Beyond automobiles, carbon fiber transformed another form of transportation even more dramatically. Carbon fiber bicycle frames can weigh under 1 kilogram, sometimes well under, creating machines that feel almost impossibly light when you pick them up. A high-end road racing bicycle frame might weigh just 700 grams, less than a liter bottle of water. This extreme lightness transforms the riding experience, making bikes feel eager and responsive, requiring less effort to accelerate and easier to carry when you're not riding. For competitive cyclists, where races can be won or lost by seconds over hundreds of kilometers, the weight savings from carbon fiber frames provide a genuine performance advantage. What makes these featherweight frames even more impressive is their strength. Such frames can still support rider loads exceeding 100 kilograms, plus the additional forces generated during sprinting, climbing, or rough road conditions. The frames don't just hold together under these loads, they remain stiff enough to efficiently transfer pedaling power to the wheels without flexing and wasting energy. Engineers achieve this by carefully orienting carbon fibers to resist loads in specific directions, placing more material where stresses are highest and less where it isn't needed. The result is a structure that's optimized in ways that would be impossible with metal tubes, with strength and stiffness exactly where needed and minimum weight everywhere else. Innovation in carbon fiber continues to produce new combinations and capabilities. Carbon fiber combined with titanium wire creates flexible, durable frames that can withstand impacts that would shatter pure carbon fiber composites. The titanium wires run through the carbon fiber matrix, creating a hybrid material that has the lightness and stiffness of carbon with improved toughness. If the carbon fiber cracks, the titanium wires prevent the crack from propagating catastrophically, allowing the structure to remain functional even when damaged. This approach has been used in some bicycle frames and other applications where impact resistance matters as much as weight savings. Two-wheeled vehicles beyond bicycles have also embraced carbon fiber extensively. Motorcycles have used carbon fiber frames since the early 1980s, though adoption has been slower and more selective than in bicycles or race cars. The higher loads and vibrations in motorcycles make carbon fiber application more challenging, and the cost-benefit analysis doesn't always favor exotic materials for street bikes. However, racing motorcycles, particularly in MotoGP and World Superbike competition, use carbon fiber extensively in fairings, wheels, and structural components. Some manufacturers have produced limited-run motorcycles with carbon fiber frames, creating machines that combine race-derived technology with street legality, though usually at prices that reflect the exotic materials and specialized manufacturing. Carbon fiber has also found applications in more mundane but equally impressive products. Ultralight ladders made from carbon fiber can support massive loads while weighing a fraction of what aluminum or fiberglass ladders weigh. A carbon fiber extension ladder that one person can easily carry might support several hundred kilograms when properly positioned. For professionals who need to move ladders frequently, firefighters, window cleaners, construction workers, the weight savings translate directly into reduced fatigue and improved safety. The ladders don't conduct electricity the way aluminum does, providing an additional safety benefit. And the corrosion resistance means they maintain their appearance and strength even after years of exposure to weather and chemicals. As carbon fiber manufacturing has matured and costs have gradually decreased, the material has spread into design elements where its visual appeal matters as much as its performance. Carbon fiber details are increasingly replacing aluminum in luxury designs, appearing in everything from furniture to consumer electronics to architectural elements. That distinctive woven appearance has become associated with high technology and premium quality, making carbon fiber a desirable material even in applications where its mechanical properties aren't strictly necessary. Watch cases, pen bodies, wallet inserts, phone cases, all of these and more are now available in carbon fiber variants, allowing consumers to carry a piece of aerospace technology in their everyday lives. Sometimes these applications genuinely benefit from carbon fiber's properties, being lighter or stronger than alternatives. Other times, the carbon fiber is primarily aesthetic, a thin veneer over conventional materials. But whether functional or decorative, the presence of carbon fiber signals quality, technology, and performance, a material once reserved for spacecraft and race cars now woven into the fabric of modern design. Carbon fiber is biocompatible and used in medical implants, which might seem surprising for a material we usually associate with aircraft and race cars. Biocompatibility means that human tissue can exist in contact with carbon fiber without rejection or adverse reactions. The body doesn't recognize carbon fiber as a foreign threat requiring an immune response, and carbon fiber doesn't leach chemicals or degrade in ways that would harm surrounding tissue. This biological tolerance, combined with carbon fiber's mechanical properties, has opened up fascinating possibilities in medical devices and implants. Materials that can live peacefully inside the human body while providing structural support are rare and valuable, and carbon fiber joins a select group that includes titanium, certain stainless steels, and specialized polymers. The applications in medicine take advantage of multiple properties simultaneously. It is found in hip replacements and dental devices, where its strength, lightweight, and biocompatibility all matter. In hip replacements, carbon fiber components can reduce the overall weight of the implant while maintaining the strength needed to support body weight and movement forces. The material stiffness can be tuned to more closely match natural bone, reducing stress shielding, a problem where overly stiff implants cause the surrounding bone to weaken from lack of normal loading. In dental applications, carbon fiber posts are used to reinforce teeth that have had root canal treatments, providing structural support that helps the tooth withstand biting forces. The posts are strong enough to do their job while being less likely to cause root fractures than metal posts. However, carbon fiber in medical and other applications does have some quirks that need careful management. Its electrical conductivity can cause galvanic corrosion when touching metals, an electrochemical process where dissimilar materials in electrical contact and exposed to moisture create a batter-like effect that corrodes one of the materials. When carbon fiber touches aluminum, For instance, the aluminum can corrode rapidly if moisture is present. This is a significant concern in applications where carbon fiber and metal components need to be joined together, like in aircraft or automotive structures. Engineers address this by using insulating barriers between carbon fiber and metal, applying protective coatings, or using fasteners and joints designed to minimize galvanic action. The issue isn't insurmountable, but it requires awareness and proper design to prevent long-term degradation. We've talked primarily about carbon fiber made from pan precursors, but there's another family worth mentioning. Pitch-based carbon fibers offer higher thermal conductivity than pan-based types, making them valuable in applications where moving heat efficiently matters. Pitch, a tar-like substance derived from petroleum or coal, can be processed into carbon fiber through methods similar to those used for pan, but the resulting fibers have different microstructures that affect their properties. While pitch-based fibers generally don't achieve the same tensile strength as high-performance pan-based fibers, they can have much better thermal and electrical conductivity. This makes them useful in heat sinks, thermal management systems, and electrodes where moving heat or electricity efficiently is more important than achieving maximum strength. Taking carbon fiber to an even more extreme scale leads to truly remarkable materials. Carbon nanotubes are nanoscale fibers far stronger than conventional carbon fiber, representing perhaps the ultimate expression of carbon's potential in fibrous form. These structures are essentially single sheets of graphene, that hexagonal lattice of carbon atoms we've discussed, rolled into seamless tubes with diameters measured in nanometers. The bonds within carbon nanotubes are perfect or nearly so, with few of the defects that limit the strength of conventional carbon fibers. Theoretical calculations suggest carbon nanotubes could have tensile strengths exceeding 100 gigapascals, more than 10 times stronger than the best conventional carbon fibers. In practice, manufacturing perfect nanotubes at useful lengths and incorporating them into composite materials remains challenging, but the potential is extraordinary. Back in the realm of conventional carbon fiber, the material continues to impress with its practical durability. Carbon fiber shows high impact and wear resistance, particularly when properly supported by an appropriate resin matrix. While carbon fiber can be damaged by severe impacts, it generally handles the kinds of wear and minor impacts that occur in everyday use remarkably well. Carbon fiber bicycle wheels roll over rough roads thousands of times without degradation. Carbon fiber drone frames crash and get back into the air. Race car components survive vibration, flying debris, and occasional contact with barriers or other cars. The material's ability to maintain its properties through repeated stress cycles and environmental exposure makes it reliable for long-term use in demanding applications. We've mentioned carbon fiber's electromagnetic properties in the context of stealth aircraft, but the applications extend much further. It can shield electronics from electromagnetic interference, protecting sensitive circuits from radio frequency noise that could cause malfunctions or data corruption. Equipment housings made from carbon fiber composites can provide structural protection while also creating a Faraday cage effect that blocks electromagnetic fields from reaching internal components. This dual functionality, mechanical protection and electromagnetic shielding in a single material, is valuable in everything from aerospace electronics to medical devices to consumer products. As our world becomes increasingly filled with electronic devices all radiating electromagnetic energy, the ability to shield sensitive equipment becomes more important, and carbon fiber provides an elegant solution. One of carbon fiber's most powerful characteristics is also one of its most challenging to work with properly. Its anisotropic properties allow engineers to tailor performance precisely, placing strength exactly where it's needed and minimizing weight everywhere else. Anisotropic means the material has different properties in different directions, unlike isotropic materials like steel that behave the same way regardless of which direction you load them. This directional nature means that a carbon fiber component can be incredibly strong in one direction while much weaker in another, if that's what the design calls for. Engineers can create structures that are perfectly optimized for specific load cases, using just enough material to carry the loads that will actually occur and no more. This optimization potential comes with responsibility, though. The material's weave direction strongly affects strength and stiffness, which means that errors in fiber orientation during manufacturing can significantly compromise a part's performance. A component designed with fibers running lengthwise might be dramatically weakened if those fibers are accidentally oriented at an angle during layup. This is one reason why quality control is so critical in carbon fiber manufacturing, and why experienced technicians are so valuable. They understand that every layer matters, that fiber orientation must be carefully controlled, and that small mistakes during manufacturing can have large consequences for final performance. The ultimate flexibility of carbon fiber lies in its engineerability. Carbon fiber can be engineered for highly specialized applications, tuned and optimized in ways that are simply impossible with conventional materials. Need a structure that's extremely stiff in bending but compliant in torsion? You can design a carbon fiber layup that does exactly that. Need something that conducts heat along one axis but insulates in other directions? Carbon fibers' anisotropic thermal properties can be exploited to create that behavior. Need a structure that changes its properties gradually from one end to another? You can vary the fiber orientation and density continuously through the part to create exactly the property gradient you need. This almost infinite adjustability, combined with carbon fiber's inherent high performance, makes it a material that's limited more by imagination and manufacturing capability than by fundamental material properties. Every carbon fiber component is in some sense a custom material, designed and built for its specific application, optimized in ways that mass-produced materials could never match. Carbon fiber transforms sporting goods through strength and vibration damping, bringing professional-level performance to equipment that everyday athletes could actually use. Before carbon fiber became widely available in sporting goods, equipment designers faced frustrating trade-offs. Make something light and it would be weak or flexy. Make it stiff and it would be heavy or transmit too much shock to the user. Make it strong and it might feel dead, lacking the lively response that athletes desire. Carbon fiber broke through these limitations, offering combinations of properties that simply weren't achievable with wood, aluminum, or fiberglass. The vibration damping characteristic is particularly valuable because it means equipment can be responsive and powerful without punishing the athlete with harsh feedback on every impact. The ability to tune flex characteristics has revolutionized equipment across virtually every sport. Fishing rods, golf clubs, and tennis rackets benefit from tailored flex profiles that would be impossible to achieve with traditional materials. A fishing rod needs to be flexible enough to cast lures smoothly and fight fish without breaking, yet stiff enough to set hooks firmly and control the fish during the fight. Different fishing techniques and different fish species call for different flex patterns. With carbon fiber, rod designers can create exactly the loading curve they want, placing stiffness precisely where it's needed and compliance where it benefits the angler. A bass fishing rod optimized for heavy cover fishing will flex very differently from a trout rod designed for delicate presentations, and carbon fiber makes both optimizations possible. In golf, the revolution has been equally dramatic. Carbon fiber golf shafts allow customized swing characteristics that help players of different skill levels and swing styles optimize their performance. A shaft needs to bend during the swing, storing energy that releases at impact to increase club head speed. But the timing and pattern of that flex must match the golfer's swing tempo and transition characteristics. Too stiff and the shaft won't load properly, leaving energy on the table. Too flexible and the shaft won't stabilize in time for solid contact. Carbon fiber shafts can be engineered with specific flex profiles, kick points where the shaft bends most, and tip stiffness characteristics that would be extremely difficult to achieve with steel. Some manufacturers create shafts with different flex patterns in different sections, stiff in some areas and flexible in others, tailored to specific swing types. Racket sports have seen similar transformations. Tennis rackets made from carbon fiber dampen vibrations better than aluminum while remaining lighter and more powerful. When a tennis ball impacts the strings, tremendous forces are generated in a fraction of a second. Some of that energy goes into propelling the ball back across the net, but some becomes vibration that travels through the racket frame to the player's arm. Repeated exposure to these vibrations can cause tennis elbow and other overuse injuries. Aluminum rackets, which dominated before carbon fiber, transmitted these vibrations harshly. Carbon fiber rackets absorb more of the shock, reducing stress on joints and tendons while still providing the stiffness needed for power and control. The material's internal damping, the way it converts vibrational energy into heat, makes the difference between equipment that punishes the body and equipment that can be used for hours without discomfort. Some sporting applications push carbon fiber to extremes that showcase its remarkable properties. Vaulting poles made from carbon fiber enable record-breaking jumps that would be impossible with older pole designs. A pole vaulter sprints down a runway carrying a long pole, plants it in a box, and uses the pole's flex to catapult themselves over a bar that might be 6 meters or more above the ground. The pole must be light enough to carry at sprint speed, flexible enough to bend dramatically without breaking, and resilient enough to return all that stored energy to launch the athlete upward. Carbon fiber poles can be tuned to specific athlete weights and running speeds, with stiffness ratings that help vaulters select exactly the right pole for their abilities. The current world records, both men's and women's, were set using carbon fiber poles that flex to seemingly impossible degrees before snapping back to straighten and propel the athlete skyward. Winter sports equipment has embraced carbon fiber enthusiastically. Carbon fiber snowboards offer sharper edge control at high speeds, remaining stable and precise when inferior boards would chatter and lose grip. At high speeds on hard snow, a snowboard experiences tremendous forces trying to deflect it and cause vibration. A board that lacks torsional stiffness will twist, causing the edges to lose contact with the snow and the rider to lose control. Carbon fiber reinforcements, often running diagonally through the board's core, provide the torsional rigidity needed to keep edges engaged even during aggressive turns at speed. The material adds minimal weight while dramatically improving high-speed stability, allowing riders to maintain control in conditions that would be terrifying on less sophisticated equipment. Water sports have found carbon fiber equally transformative. Carbon fiber kayaks are significantly lighter and more maneuverable than those made from traditional materials, turning vessels that were once awkward to transport and sluggish to paddle into responsive craft that feel alive under the paddle. A lightweight kayak accelerates more quickly with each paddle stroke, requires less effort to maintain speed, and can be carried to and from the water without requiring heroic strength. For racing kayakers, the weight savings translate directly into faster times. For recreational paddlers, a lighter kayak means less fatigue and more enjoyment. The stiffness of carbon fiber also means that paddle power translates more efficiently into forward motion rather than flexing the hull, another performance advantage that paddlers can feel with every stroke. Perhaps the most inspiring application of carbon fiber in sports involves athletes overcoming physical challenges. Prosthetic limbs made from carbon fiber return energy efficiently to runners, creating spring-like prosthetics that store energy during the stance phase and release it during toe-off. These running-specific prosthetics, sometimes called blades because of their curved shape, have enabled amputee athletes to run at speeds that approach or even match able-bodied runners. The carbon fiber flex and return characteristics are carefully tuned to the individual athlete's weight, running style, and competition distance. The material's high strength-to-weight ratio allows the prosthetic to be light enough not to cause fatigue while being strong enough to handle the forces of elite-level running. Stories of Paralympic sprinters pushing world-class speeds on carbon fiber prosthetics demonstrate not just the material's capabilities but its potential to change lives. Beyond sports, carbon fiber has found unexpected applications in music. Acoustic instruments made from carbon fiber resist humidity-related distortion that plagues wooden instruments. Traditional acoustic guitars, violins, cellos, and other wooden instruments are sensitive to temperature and humidity changes. Wood expands when humid and contracts when dry, affecting the instrument setup and potentially causing cracks or warps. This sensitivity means that wooden instruments need careful climate control and regular adjustments. Carbon fiber instruments remain dimensionally stable regardless of humidity, making them ideal for musicians who perform outdoors, travel frequently, or live in climates with high humidity variation. A carbon fiber guitar can go from an air-conditioned room to a humid outdoor stage without going out of tune or requiring setup adjustments. The tonal characteristics of carbon fiber instruments have improved dramatically as manufacturers have learned to work with the material. Carbon fiber cellos maintain consistent sound quality across climates, sounding the same in dry winter air as in humid summer conditions, something no wooden cello can claim. Early carbon fiber instruments often sounded bright and lacked the warmth of wood, but modern designs have addressed these issues through careful attention to acoustic properties. Manufacturers vary the thickness, stiffness, and damping characteristics of carbon fiber composite structures to create tonal qualities that musicians find pleasing. While purists still prefer traditional wooden instruments for their unique sonic signatures, carbon fiber instruments have carved out a respected place in the musical world, particularly among traveling musicians, outdoor performers, and anyone who values consistency and durability alongside sound quality. The marriage of ancient acoustic principles with space-age materials creates instruments that honor tradition while embracing the future. Asia produces the majority of the world's carbon fiber, dominating an industry that was largely pioneered in the United States and Europe. Over the decades, manufacturing capacity has shifted eastward as Asian companies invested heavily in production facilities and developed expertise in carbon fiber manufacturing. This shift mirrors broader trends in advanced materials and manufacturing, where initial innovation happens in one region but large-scale production eventually concentrates wherever the combination of technical capability, infrastructure, and economics is most favorable. Today, if you're using a product that contains carbon fiber, there's a very good chance that fiber was produced somewhere in Asia, even if the final product was assembled elsewhere. Within Asia, one country stands out as particularly dominant. Japan supplies roughly half of the global carbon fiber market, a remarkable achievement that reflects decades of investment in materials science and manufacturing technology. Japanese companies like Torii, Taigen, and Mitsubishi Chemical have become household names in the carbon fiber industry, known for producing high-quality fibers and continuously pushing the boundaries of what's possible. These companies didn't just build factories, they developed entire ecosystems of suppliers, equipment manufacturers, and technical expertise. The Japanese dominance in carbon fiber production is so complete that many manufacturers worldwide use Japanese-made fibers even when they're competing against Japanese companies in final products. However, the carbon fiber industry isn't monolithic, and different producers have adopted different strategies. Some countries focus on high-cost performance carbon fiber production, emphasizing efficient manufacturing and competitive pricing rather than only chasing the absolute highest performance grades. This approach recognizes that not every application needs aerospace-grade carbon fiber with maximum stiffness and strength. Many applications, sporting goods, automotive components, consumer products, can use slightly lower performance fibers at significantly lower costs. Countries like China have invested heavily in this segment, building large-scale production capacity aimed at making carbon fiber affordable enough for mass-market applications. This democratization of carbon fiber, making it economically viable for everyday products rather than just exotic applications, is expanding the market and driving innovation in manufacturing processes. The scale of global carbon fiber production is genuinely impressive. Annual carbon fiber output could wrap around Earth more than 1,000 times if you laid all those fibers end to end. Think about that for a moment. We're producing enough carbon fiber each year to circle the planet 1,000 times over, and that production continues to grow year after year. Each individual fiber is impossibly thin, yet collectively they represent hundreds of thousands of tons of material, all carefully manufactured in controlled processes that transform polymer precursors into high-performance structural fibers. This industrial capacity has built up over decades, and it continues to expand as new applications emerge and existing applications grow. The financial side of the industry reflects this growth and potential. The global carbon fiber market is expected to exceed $10 billion by 2030, representing substantial growth from current levels. This expansion isn't just about selling more of the same products to the same customers. It's about carbon fiber penetrating new markets, solving new problems, and becoming economically viable in applications where it was previously too expensive to consider. As manufacturing costs decrease through economies of scale and process improvements, the threshold for where carbon fiber makes economic sense keeps shifting. Applications that couldn't justify carbon fiber's cost 5 years ago might find it competitive today, and users that seem too expensive today might become viable in a few more years. A major driver behind this market growth is the transformation of transportation and energy systems. Demand is driven by electric vehicles and renewable energy systems, two sectors that are growing rapidly and have specific needs that carbon fiber addresses well. Electric vehicles need to be as light as possible to maximize range from their batteries, making carbon fiber's weight savings particularly valuable. As battery technology improves and costs decline, the remaining path to better electric vehicles runs through weight reduction, and carbon fiber is one of the most powerful tools available. Every kilogram saved in vehicle structure is a kilogram that doesn't need to be accelerated, doesn't need to be braked, and doesn't drain the battery during every mile of travel. Renewable energy systems have embraced carbon fiber for somewhat different reasons. Wind turbine blades use carbon fiber for strength in harsh conditions, creating structures that must span tremendous distances while remaining light enough not to overload the tower and bearing systems. Modern wind turbines have grown to immense sizes, with blade lengths exceeding 80 meters on the largest offshore installations. These blades operate in brutal environments, exposed to continuous cycling loads, temperature extremes, moisture, salt spray, and occasional impacts from ice or debris. They must last for 20 years or more with minimal maintenance. Carbon fiber reinforcements, typically concentrated in areas of highest stress like the spar caps that run the length of the blade, provide the strength needed to survive these conditions while keeping weight manageable. Without carbon fiber, the largest modern turbines simply wouldn't be possible. Carbon fiber has also made inroads into infrastructure, an industry traditionally dominated by steel and concrete. Carbon fiber reinforces bridges, tunnels, and concrete structures, often as part of repair and strengthening projects rather than new construction. Existing structures that need to carry heavier loads or that have deteriorated over time can be strengthened by bonding carbon fiber sheets or wraps to critical areas. The carbon fiber adds tensile strength without adding significant weight or requiring major modifications to the structure. Bridge columns can be wrapped with carbon fiber to improve their earthquake resistance. Concrete beams can be reinforced on their bottom surfaces to increase their load-carrying capacity. Tunnel linings can be strengthened without reducing clearances. These applications take advantage of carbon fiber's high strength, corrosion resistance, and ease of installation compared to traditional strengthening methods. Even solar energy systems benefit from carbon fiber's unique properties. Solar panel frames benefit from its lightweight durability, particularly in large installations where the mounting structure represents a significant portion of total system cost and weight. Lighter frames mean less structural support needed, which means lower installation costs. Corrosion resistance means longer system life with less maintenance, improving the economics over the decades-long lifespan of solar installations. And dimensional stability means solar panels maintain their precise orientation regardless of temperature variations, ensuring optimal energy production. As solar power continues to expand globally, the cumulative demand for mounting structures creates a substantial market for materials that can reduce costs while improving performance. Looking at the bigger picture, carbon fiber continues to expand into new industries and technologies, finding applications that weren't even imagined when the material was first developed. From the earliest light bulb filaments through aerospace applications that define the modern carbon fiber era, and now into everyday products and infrastructure, the materials journey has been one of continuous expansion. Each new application teaches us something about carbon fiber's capabilities and limitations, informing the next generation of designs and manufacturing processes. Research continues into new precursor materials, new manufacturing techniques, better recycling methods, and novel composite architectures. Carbon nanotubes and graphene represent possible future directions where carbon's potential in fibrous and sheet forms might be pushed even further. But even with conventional carbon fiber, we're still discovering new uses, new combinations with other materials, and new ways to optimize designs. The story of carbon fiber isn't finished, it's still being written, one innovation at a time, one application at a time, as this remarkable material woven from humanity's most fundamental element continues to shape the technologies and structures of our modern world.